right. So the recording going. Well, let's go ahead and take a look at our class. All righty. Process that scientists go through in order to figure out how many of the atoms that we're dealing with on either side of an equation is called balancing chemical equations. Balancing the number of atoms on the reactant side, that starting side, with the number of atoms on the product side, our kind of finished produced substances that we are dealing with. Let's go ahead and jump on in here. All right. So you may remember from yesterday, and by yesterday, I mean Tuesday, last class, that chemical changes and chemical reactions are all about taking one set of substances and turning it into something new. There we go. So if you remember from Tuesday, our starting materials, our substances that are going to react together, are called our reactants. And the things that are produced, our ending materials, the things we end up with, are called the products. Again, very creative names here from scientists. Reactants are what react together. Products are what are produced. So if you want to think of it kind of like similar to a math equation, the reactants are in front of equal sign, and then this arrow kind of acts like our equals, and then the products are at the end. They are made in that chemical reaction. Hey, Irma, no worries. Good to see you. Thanks for being here and hopping on.
Sorry, thank you.
No worries. Thanks for being here. So this is sort of the most basic idea of a chemical reaction. We start off with one set of substances, one set of things, and we turn it into something new, something different. And so for an example of that, we looked at that photosynthesis equation from the other day, right? So the first thing we looked at was that the reactants and the products are different, right? We have carbon dioxide and water on one side, and then glucose, this big 6-carbon sugar molecule, and oxygen on the products side. So these guys and these guys are not the same. We have different substances that we're dealing with. So that's kind of our first point on chemical reactions. We're making new, different things and the products. And the second point that we pointed out yesterday is that we cannot create or destroy any atoms, meaning that we have to have the exact same set of atoms on the reactants and product side of the equation. So like on the reactant side, for example, we have carbon, we have oxygen, and we have hydrogen, C's, O's, and H's. And that means that on the product side, we also need to have C's, O's, and H's. So we didn't add in any new atoms, right? There's no nitrogen, there's no iron that all of a sudden appeared in the products. And we also didn't take away anything, right? We have 3 different atoms on the reactants. We need to have those same different atoms on the products. We can't get rid of oxygen or get rid of hydrogen. We have C's, O's, and H's on the reactant side. We need to have C's, O's, and H's on the product side. What we can do is move them around, rearrange them into different shapes, different forms. So like before, we had a whole bunch of carbon dioxides. And so we took a whole bunch of those carbons and put a bunch of hydrogens and oxygens on them in order to form this big glucose molecule. So we just rearranged the atoms that we already had. They're bonded to each other in different ways over on the product side, right? That's what makes it a new substance. We changed around those chemical bonds. We broke some covalent bonds. We added on some covalent bonds. And so now we have a big glucose molecule and some leftover oxygens. So those were kind of the two main things that we talked about when it comes to chemical reactions on Tuesday, right? We make new things in the products. So our products and reactants are different from each other. And we can only rearrange the atoms. If we have 3 types of atoms on one side, we have to have those exact 3 types of atoms on the other side. They can be attached differently. They can be in different numbers from each other. We just have to have the same types. All right, so does that sound pretty familiar to everybody? Anybody have any questions or anything that you're still a little bit confused about when it comes to these chemical reactions?
No.
No.
All right. So the thing that we are going to be focusing on today, that's a little different, like I said, is making sure we actually have the same number of atoms on the reactant side as we do on the product side. And there's a specific way that we go about this, which we'll talk about in a second. But the first thing is to recognize what can be changed in a chemical reaction and what cannot. So a chemical equation, just like this photosynthesis equation right here, is the way that scientists like to write out chemical reactions. We use chemical symbols and formulas instead of like writing out the whole name of the molecule, just to make it really clear which atoms are dealing with which. So you could write this photosynthesis equation as the words carbon dioxide plus water turns to glucose plus oxygen, but that doesn't tell you a lot about exactly the atoms that are in the reaction. So instead, scientists like to write CO2 plus H2O gives us C6H12O6 plus O2. That would be kind of our base photosynthesis equation. So in that equation, you may have noticed that there are these big 6's in front of some of these types of molecules, some of these atoms. And those big numbers, those big 6's, it's science, so of course they get their own special name. They are called coefficients. So if there's nothing else that you remember from class today, remember coefficient. It's the big number before the chemical symbol, and it represents how many units we have of each substance. So for example, in our photosynthesis equation, we have 3 coefficients written out. Right, we have a 6 in front of the CO2. We have a 6 right here in front of the H2O. And we have a 6 over here in front of the O2. These 3 are our coefficients in this equation. And a coefficient tells us how many of each molecule, how many of each compound are in the equation. So for example, in photosynthesis, these numbers tell us that we need 6 carbon dioxide molecules. So we need 1, 2, 3, 4, 5, 6 molecules of carbon dioxide and 6 molecules of water, 6 molecules of H2O to react together. And those will give us 1 molecule of glucose. So if there is no coefficient formally written out in the front of the molecule, that just means that that's the only one that there is. So we have 6 carbon dioxides and 6 waters, but we've only got the 1 glucose. And then we also have some 6 oxygen molecules, some 6 O2s left over as well. So this is how many of each molecule we have in the chemical equation.
We'll stop you right there. With our homework, does it show any numbers?
Aha. So Robert brought up the point that if you look at the homework, you may have noticed that none of those equations have numbers. And that's because our job today is going to be to figure out which numbers go in those equations. So the ones that we're going to be starting with today and the ones on the homework that we're going to be doing as examples are the base sort of equation. Like it would be if you just had CO2, H2O, glucose, and O2. And then our job is going to be to fiddle around with the coefficients, fiddle around with these numbers, and make it so that we balance the number of reactant side atoms and the number of product side atoms. So on the homework, there are no coefficients on there yet because we have to go in and add them. And today we're going to talk about how you figure out what are the correct coefficients to add. So these numbers, these big numbers right here, these are our coefficients. And like Robert was just referring to, when we're balancing the chemical equations, these are the numbers that we are allowed to mess around with. We can fiddle with them, we can make them bigger, we can make them smaller, depending on what the equation needs. You may have noticed that there are also some other little numbers in our equations. These guys are called subscripts. So the 2 in CO2, or the 2 in H2O, or the 6-12-6 in C6H12O6.
The highest you can go with the number?
Not necessarily. You can go even higher if you make a really, really big molecule. So these guys down here are called subscripts. They just represent how many of a specific atom are in this one molecule. So like, for example, we all know that water, the symbol for water is H2O. And that little 2 tells us that there's 2 hydrogens and 1 oxygen that come together to make a water molecule. Just like carbon dioxide over here, this 2 tells us that there's 1 carbon and 2 oxygens that come together to make carbon dioxide. These subscripts are part of the chemical formula, and that means that they are permanent. They are like set in stone or written down in Sharpie. We are not allowed to touch them when we're going to go in and try to balance out the chemical equations. So anytime that you have any subscripts in your equation, they're going to be there the entire time. We can't make them any bigger. We can't make them any smaller. We just have to deal with them the way that they are. So the coefficients, the big numbers at the front, these we can change. These we can adjust and deal with in order to balance our equations. These subscripts down here, these we cannot change. We are not allowed to touch those during the balancing process. They have to stay the same throughout the entire process. All right, so before we move on into actually talking about the balancing chemical equations, does anybody have any more questions about the coefficients, the subscripts, or what's going on in our chemical reactions so far?
No, sir.
All righty. So like I said, the goal that we're going to be trying to accomplish with today is making what are called balanced chemical equations. Meaning that we're going to shuffle around our coefficients, those big numbers at the front of the molecules, so that the number of atoms of each element are the same same number on both sides of the equation. So for example, in our photosynthesis equation over here, we're trying to make it so that there's the same number of carbons, the same number of C's on the reactant side and the product side. And then we also want there to be the same number of O's on the reactant side and product side. And we want there to be the same number of H's on the reactant side and the product side. So that's going to be our goal today, making sure that each atom has the same amount, the same number on the reactant side of the equation and the product side of the equation. And the way that we can do that, the way that we're going to be figuring that out, is by messing around with these coefficients, changing them to give us the numbers that'll make everything balanced. So the general steps in the balancing process go like this. You're going to have the chemical equation. So like what Robert was saying earlier, you're going to have the base equation with no coefficients in it. You're going to write out, to start off with, how many of each atom are on the reactant and product side. So you're going to see, are we balanced already? Spoiler, none of the equations we're dealing with today are balanced. If they were, we wouldn't need to work with them. So when they're not balanced, we see which ones are unbalanced. We can choose the coefficients that we think will help balance the equation. Once we've changed the coefficients, figured out now how many do we have, we'll go back, recheck the numbers of each atom, and see if we have successfully balanced the equation, made it so that the C's, H's, and O's on one side all match up with the C's, H's, and O's on the other side. So it's kind of hard to understand when I just put it into words like that and kind of explain it. So I'm going to take you guys through a really simple example and show you kind of exactly step by step how you work through this process. How to balance the thing correctly. So here is our base chemical equation. HGO, mercury oxide. So mercury is one of those weird ones where the name is mercury, but the symbol is Hg. I don't know why, it just ended up like that. Mercury oxide produces or turns into mercury plus oxygen. HGO produces Hg plus O2. So that is our base chemical equation. So the first thing that we've got to do is figure out how many of each atom do we have on the reactants and product side of the equation. So on either side of this arrow, how many Hg's and how many O's do we have? So if you look at the Hg's first, we can see that we have one Hg over here on the reactants, this guy right here. And we have one Hg over here on the products, this guy right here. All right, now let's look at the O's. So this is usually what I like to do. I like to write down the symbols of the atoms we're dealing with, and then make like a little chart of how many there are. So we have one Hg and one Hg on either side. We have one oxygen right here, one O on the reactant side, and two oxygens on the product side. So this little subscript 2 down here tells us that there's two oxygens, two O's over here on the products. So let's check for the balance. Hg, 1 and 1. So 1 and 1 are the same. So the Hg's are balanced. That's good. O's, 1 and 2. The oxygens are not balanced. We have one oxygen on the reactant side. We've got two oxygens on the product side. That is no good. This is an unbalanced equation. So we've got to do something with these oxygens to try and make the equation balanced. Remember, you are not allowed to touch this 2 over here. This is permanent, set in stone, not to be messed with. So if we can't make this 2 smaller into like a 1, maybe we can change this 1 and make it into a 2. So the only thing that we're allowed to do is mess with the coefficients. And on the product side, the only place that we can put a coefficient is here. So that's an important thing to note. Coefficients cannot go into the middle of a compound. Like you can't put a 2 right in the middle here and be like, oh, Hg, 2 O's, we're all set. This guy is one piece, one unit bonded together. So the coefficient has to go out front right here. So if I want this oxygen to be a 2 instead of a 1, I can fill in a 2 right here. So I'll add a 2 to my reactants in order to help balance out the oxygen. So now we have 2 oxygens on the reactant side. Yay! 2 and 2. Those guys are balanced now. Hooray. But when we put this 2 right here, it applies to both of the elements. It applies to the O and to the Hg. So while we might have 2 oxygens now, which is good, these guys are balanced. 2 O's on one side, 2 O's on the other side, all good. But now, whoops daisy, we have 2 Hg's on the reactant side and only 1 on the product side. We've balanced the O's, but the Hg's are no longer balanced. There's 2 over here and 1 over here. This will happen a lot when you're balancing equations, and it is totally okay. It's a very, very normal part of the process. Because now we say, okay, we balance the oxygens, and that's good. So now what can we do to balance our Hg's? Well, we know we want to leave this 2 right here because it made our oxygens balanced, and we don't want to do anything to mess up our oxygen balance. So if this guy is a 2 and this guy is a 1, maybe we can do something over here to make this Hg be a 2. I'm thinking we put a coefficient of 2 right in front of our Hg friend right here. So let's do that. We'll add a 2 to Hg on the product side. And now let's double check. It looks balanced. I want to make sure. We have 2 Hg's on the product side, or on the reactant side, excuse me. So 2 Hg's on the product side. So that's good. 2 and 2 are the same. We have 2 O's on the reactant side from right here, and 2 O's on the product side right here, 2 and 2. So those are the same as well. So now we have a balanced chemical equation. So our final result, our final answer is 2 HgO produces 2 Hg plus O2. 2 mercury oxide produces 2 mercury plus an O2. So that is how the basics of how we make a balanced chemical equation. We figure out how many atoms are of each type on the reactants and product side. We change a coefficient to try and make things balanced, and then see where that takes us. If it leaves us with another unbalanced situation, we can go in and change another coefficient and see if that helps bring things back to being balanced. The other thing that I will say is that it doesn't matter that Hg and O happen to have the same number here. So this number and this number doesn't matter if they're the same. This number and this number doesn't matter that they're the same. All that matters is that the HG numbers match up on either side and that the O numbers match up on either side. So this is balanced, not necessarily because everything is 2, but because the HGs are the same and the O's are the same. That's what makes it a balanced chemical equation. All right, so I know that was a lot of stuff that we just went over in that example. We are going to do a whole bunch more examples to kind of get you guys more comfortable with doing this. But for right now, are there any immediate questions that anybody has, or anybody completely confused as to where any of these numbers came from?
I am.
I am 100% confused.
All right, that is totally
Yeah,
okay.
me too. I have no idea what's going on. Yeah, I'm lost.
All right, well, let's try and do another example together. And maybe I'll have you guys help me out a little bit as we go along and see if that kind of helps things a little bit. One more thing that I want to mention before we move along, and that is if you have a element that has a subscript, so a little number down here, and you have to put a coefficient in front of it, whenever a coefficient like this big 3 and a subscript like this little 2 down here interact, you're going to multiply them. So that's the only real math besides like some counting that you need to know in order to do this, is that if you have a big number that interacts with the little number down here, you multiply. So for example, if we have 3 O2 molecules, 3 times 2 is 6, so we have a total of 6 oxygen atoms. If we have a little bit bigger molecule like water, H2O, and we have 4 H2O molecules, the 4 applies to the H and the O equally. So 4 H2s, 4 times 2 is 8. So that'll give us 8 hydrogen atoms. And then O doesn't have a subscript, so there's only the one O. So 4 O's gives us a total of 4 oxygen atoms. So we'll do an example where this is a bigger deal, but I just wanted to introduce it right now so that you catch it when it comes up later. Whenever you see a coefficient big number and a subscript little number, and they're going to interact with each other, you multiply in order to find the total. All right, so let me pull some examples from your homework that we can work on together to kind of make sure that everybody is on a good page. That's okay. I'm going to bring up a whiteboard here for people to take a look at. All right, let me see here. Present, window, whiteboard. Let me see which one that I want to do with you guys. All right, so let me go ahead and pull the first example from the homework. We've got, so on the homework, you'll see these blanks in front of the atoms, and those represent areas where you can mess with the coefficients. All right, so another relatively simple example, Ca, calcium, plus O2, oxygen, is going to react together and it's going to produce calcium oxide, CaO. So Ca is one of our atoms, so I'm going to write that down here, Ca. And oxygen, O, is our other atom. So I'm going to write that down here as well. All right. So the first thing that we're going to do is count up how many atoms we have on each side to start. So remember, over here is our reactant side. And on the other side of the arrow is our product side. So looking over at our reactant side atoms, how many Ca atoms do we have?
Oh,
One.
One. Exactly. Just this guy right here. So we got one Ca on the reactants. How many oxygens are over here on the reactant side?
Two.
Two. Bingo. Two, because this guy right here. So we've got one Ca and oxygens over on the reactants. Now, if we take a look over on the product side, how many Ca do we have?
What does this mean?
One.
What was that?
No balls. No skipping turns. No turns.
One.
One, exactly. We still only have the one Ca. So this guy right here is one Ca atom. And then what about our oxygen? How many O's do we have?
One as well.
Robert's got it as well, and same in the chat. Yep, one as well. One Ca and one O in the product. Yeah, so remember, we're splitting it up by how many on, so this arrow is like our dividing line right here. We have one Ca and two O's on the reactant side. And this guy does not have any coefficients or any subscripts, so there's just one Ca and one O on the product side. Yeah, Estrella, go for it.
Is that how the layout is supposed to look? Because that's not how my layout looks on in the docs.
On the doc, it should look, hold on, let me pull up an example. It should look something like,
yeah.
let's see. Okay, that's better. So the doc should look something like this.
Okay, it does. It's just it just looked different the way you wrote it, but it looks like that.
Yeah, so yeah, the way I wrote it might look a little bit different, but it's the same idea where you have a spot for the Ca and O on one side and a spot for the Ca and O on the other side. On my example, I just made it so that I didn't have to write these guys, the Ca and O, multiple times. All right, thanks for checking though and letting me know. Okay, now I've got to jump away from there and go back to the whiteboard. There we go. All right. So to start off with, our CAs look like they're balanced. We have one on the reactant side and one on the product side. So that's a good sign. Those 1 and 1. But our oxygens are not equal. We have 2 over on the reactants and 1 over on the products. So these are not equal, which means we have a balanced equation. This equation is unbalanced. There's not the same number of O's on both sides.
So take it away.
Yeah, Gerson, go for it.
So we need to add a coefficient of 2 on the reactor side? Or no, or on the product side?
Well, oh, I think, yeah, that could be a good thought. So, as Gerson, I'm assuming, noticed, we have 2 and 1, but remember, this 2 is a subscript, and you're not allowed to touch it. So there's nothing that we can do to this oxygen in order to make it go down. That 2 is permanent. But there is something we could do over here to make this oxygen go up. And as Gerson suggested, we could put a 2 coefficient right here. So now we don't have 1 CaO, we have 2 CaOs. So this 2 is going to apply to this oxygen right here. And so now we have not 1, but let's cross that out, 2 O's over on this side, on the product side. So that's good. That accomplished what we were trying to do. That balanced out our oxygens. But also, always remember that 2 also counts towards the calcium, the Ca. So we also have now made it so now we have 2 CAs on the product side. So we made our oxygens equal. Yay, we did it.
All 2.
But our CAs now are unbalanced. We have 1 on the reactant side, but thanks to this coefficient right here, we've got 2 on the product side. So I don't want to mess with this 2 anymore because we used it to make our oxygens balanced, and that was good. So is there something that we could do over on the reactant side to help balance out with our 2 CAs? Is there anything we can do on the reactant side, on the left-hand side over here, that'll give us 2 CAs just like the product side?
Add a big number.
Mm-hmm. And what big number should we add?
2, right?
Yep, I would recommend adding a 2. We can put a 2 right in front of our lone CA over here. So now we don't have 1 CA anymore because we put this 2 coefficient here. Now we've got 2 CAs on our reactant side.
What is the big number called again?
A coefficient.
Okay, so it's still called a coefficient. Okay.
Write that down here.
So the little ones are called coefficient 2 or no?
Nope. The little ones are called
Okay. Subscripts.
think of sub like submarine or subterranean, like it goes under, it goes beneath. So the coefficients are the big number that goes next to the atom. The subscripts are the little numbers that go kind of underneath it. Great question. So now it looks like we're balanced, but I'm going to check and make sure. We have 2 CAs over on the reactant side, and we've got 2 CAs over on the product side. So that's balanced. That checks out. We've got 2 O's over on the reactant side. So this guy never changed. And we've got 2 O's over on the product side. So that checks out as well. The CAs are the same. The O's are the same. So now we have a fully balanced chemical equation. So our final answer here is 2Ca plus O2 produces 2CaO. 2 calcium plus oxygen produces 2 calcium oxide. So we figured out, to start off with, how many of each atom are on the reactant side and product side. We noticed that the O's were unbalanced, so we changed this coefficient to a 2 in order to try and balance the 2 O's. We did that, but in the process, we made it so that there were 2 CAs on the product side. That was unbalanced. So then in order to balance the CAs, we added this 2 coefficient over here. And that made the CAs balanced as well. So balanced CAs and balanced O's gives us a fully balanced chemical equation. All right. Anybody have any questions? Anything that we just went through where you're still not really sure where some of these numbers came from?
Do you like just pick the number 2, or how do you get the big number 2?
So to start off with, we had 2 oxygens on the reactant side and 1 on the product side. So we started like this, right?
Yeah.
And so I was thinking that if I want my oxygens to be balanced, I could put a 2 here, and that would cause me to have 2 oxygens on the product side. And so when I put that 2 here, it gave me the 2 oxygens, and that's what changed this into a 2. So I picked the number 2 because I thought that would give me the best chance or the correct way of matching up with this number 2 right here.
Okay, I get it now.
Awesome. And Robert asked a good question a little bit earlier as well. He asked about this oxygen right here. And if you don't need to do anything with the coefficient, if you make it to this balanced stage right here, and you never had to change the coefficient on oxygen, you can just leave it blank. You don't have to fill in anything, and that will tell me that only this one O2 hanging out right here. So if by the end of the equation, if everything's balanced and there's one that's blank, that is totally fine. All right, good question. Any other questions about how we got to some of these results?
I have a question. Is balance the same as like making it even, right? Like, is it always going to be an even number on the product side?
So it'll always be, for a balanced equation, it'll always be the same number on the reactants and product side.
Okay.
So again, 2 and 2. These guys are the same, so Ca is balanced. 2 and 2. These guys are the same, so O is balanced. It doesn't matter if this was 3 and 5, or if this was 1 and 7, as long as they match on either side. When all of them match, that is when you have a balanced equation.
Okay, thank you.
No problem. So I'll actually go ahead and move on to the next example, because it actually provides a really nice kind of way of showing how you can get different numbers of these atoms. So that was a pretty simple example. It's really similar to the one that we started off with at first. This next example is going to bump things up a little bit in terms of the complexity. So I'm really going to need you guys to help me out with this one. So our equation looks like this. It's the second equation from your homework. And it says that if we take some nitrogen, N2, and combine it with some hydrogen, H2, we are going to make some nitrite, NH3. So nitrogen plus hydrogen produces nitrite. N2 plus H2 produces NH3. So the first thing that we have to do is figure out our atom numbers. So we have N's and we have H's. That's our two atoms. So we've got N's, we've got H's. We have the reactant side over here, and we've got the product side over here. So starting off on our reactant side over here, how many N's do we have to start off with?
1.
So it's not 1, it's actually based
2.
on this right here, which tells us, yep, we've got 2 N's. So remember, always look to the subscript at first if you want to figure out your number of atoms. N2 means we've got 2 nitrogens that are bonded together. What about hydrogen? How many hydrogens are we starting off with?
Two.
2, exactly.
Yeah.
And yeah, 2 hydrogens.
I need to say that again on
No, that's okay. All right. Up next, we're going to go over to our product side. So we figured out correctly 2 nitrogens and 2 hydrogens on the reactant side. Over on the product side, how many nitrogens do we have?
Isn't it 1?
Exactly, it is 1. So NH3 means that we've just got 1 nitrogen atom, but that 1 nitrogen is bonded to how many hydrogens?
3.
3, precisely, perfect job. So we've got 1 nitrogen and 3 hydrogens in the product side. So this is very obviously not a balanced chemical equation. The N's are not the same. We have 2 and 1. That's not equal. And the H's are not the same either. We've got 2 and 3. Oh boy. What a predicament. So on the previous examples, it was clear where to start because one of them was balanced already and one of them was not. This one is a little less clear. So in cases like this, my recommendation, what I always try to do, is start off with the smaller numbers. start off with whichever atom is there in the smaller amounts, see if that's easy to figure out, and then kind of work up from there. So in this case, there's only 3 total N's to start off with, but there's 5 total H's. So I think we should start off with trying to balance our nitrogens and then see where we go from there. So we have 2 nitrogens on the reactant side and 1 nitrogen on the product side. Again, we cannot do anything with this 2 right here. We can't make it bigger or smaller. It's stuck as a 2. So if we can't make this 2 smaller, can we do something with this 1 and turn it into a 2?
Yes, you can make it a 2, I believe.
All right, so what should we do over on the product side to give us 2 nitrogens?
Couldn't you put the 2 in front of the N?
Exactly. NH3 is the 1 molecule over here. So we can put a 2 coefficient down in front of it. So now this 2 is going to give us 2 N's, just like we were looking for. So that's a good sign. It looks like we have equaled out our N's a little bit. That's nice. But when you have this 2 that's going to take our nitrogen from 1 nitrogen to 2 nitrogens, don't forget, it's also going to come over here and mess with this hydrogen as well. So does anybody remember what we do when we have a coefficient big number and a subscript small number that interact with each other? You can't, so as Robert's saying, you can't touch the 3 directly. Well, what happens when a coefficient and a subscript meet? What do you do when you guys interact?
You multiply.
Multiply, bingo, he remembers. So 2 times 3 is going to give us 6. So when we put a 2 in here, we're doubling the number of nitrogens and we're doubling the amount of hydrogens. So we have 2 nitrogens where we had 1 before. And then we have 2 times 3 gives us 6 hydrogens over here on the product side. So our nitrogens are balanced. Hey, we did it. Good job. Hydrogens, though, still not balanced, still not the same. That might be an issue. So I'm thinking, I don't want to do anything more on the product side. We already balanced our nitrogens, and it caused us to get this big number of hydrogens. So can we do something over on the reactant side that'll give us 6 hydrogens? Is there any way we can mess with the coefficients over on the reactant side to give us 6 hydrogens instead of 2 hydrogens?
Can you add a coefficient 3?
Yes, you sure can. So this is a 2, and we know that we're trying to get to 6. And so if we make this coefficient a 3 right here, 3 times 2, because remember, coefficient and subscript means you multiply, you times. 3 times 2 gives us not 2, but 6 hydrogens. So this is looking promising. I think we've just about balanced it, but let's double check and make sure. We've got 2 nitrogens over here on the reactant side and 2 nitrogens on the product side. So that checks out. That's balanced. We have 3 times 2 is 6 hydrogens on the reactant side. And 2 times 3 is 6 hydrogens on the product side. So that checks out. So this is our fully balanced chemical equation. N2 plus 3H2 produces 2 NH3. Nitrogen plus 3 hydrogens gives us 2 nitrites, 2 NH3 molecules. So again, we followed the exact same series of steps as last time. We just did it with a little bit different numbers. We figured out to start off with how many nitrogens and hydrogens do we have. We had 2 and 1 nitrogens and 2 and 3 hydrogens. We took a step to try and balance it by messing with the coefficient. In this case, like I said, I recommend starting off with the smaller numbers. And so nitrogen had the smaller numbers. So we put the 2 coefficient over here to give us 2 nitrogens over here. When we did that, it changed our hydrogen numbers. But luckily, we were then able to come over here and put a coefficient by this hydrogen over here, this H2, to give us our fully balanced hydrogens. So once you get set up, it's all about change a coefficient, try to balance one of your atoms, and see what happens with the other atom. All right. Anybody have any questions about this example? Anything where you're not really sure where any of these numbers came from or how we figured out the coefficients that we're going to need?
How did you get 6?
So hold on, where's my mouse? There we go. The first 6 we got because we tried to balance our ends over here, which is why we put 2. Because we started off with 1 n. We wanted to make it 2 n's. So we put the 2 coefficient here. That gave us 2 n's. But this 2 also interacts with the H. And H and NH3 has a subscript of 3. And so we did coefficient times subscript. Whenever you see them come together, you're always going to do multiplication for the coefficient and the subscript. The coefficient was 2. The subscript was 3. And 2 times 3 is equal to 6.
Okay.
And then on the reactant side, we did the exact same thing, just with the numbers flipped. In this case, we had a coefficient of, or a subscript of 2. We added a coefficient of 3 to try and make sure that the H is balanced. And so we had a coefficient of 3 times a subscript of 2, gave us a total of 6 H's on this side as well.
Okay, so you always multiply when it's the 2 numbers like that. So whatever numbers are there, you multiply them. Okay.
Exactly. Whenever you have a big number coefficient and a little number subscript come together, you multiply. All right, great question. Any other questions about this particular example? We're going to do one more together, but is anybody still really confused about where any of these numbers are coming from?
So the number, yeah, I'm looking at 3. So the numbers in the middle of a U and an O, does that little 2 works with the number on the left and the number on the left?
Just the one on the left.
This one.
And so, yeah, so we'll show that example. But yeah, so what Robert was just asking about is if you have lots of these atoms with subscripts on them, then which one does the subscript go to? Like if this N had like a, I don't know, like a 4 down here or something, the subscript is always going to go with the atom on the left. So like in this example over here, the 3 only goes with the H, nothing else. So even if there was like, I don't know, O or something over here for whatever reason, it was NH3O,
So it turns.
the 3 only goes with the H. These two are what go together. And we'll actually see an example of that in our very next question, which I think is what Mr. Robert was referring to. Third question on the homework and last example that we're going to do together today is a little bit trickier once again, because now we're going to work with 3 atoms. Cu2O, copper oxide, Cu is copper, plus carbon gives us copper and carbon dioxide, CO2. So we have our 3 atoms. We have copper, we have oxygen, and we have carbon. So we've got the reactant side, we've got the product side. So on our reactant side over here on the left-hand side, how many copper atoms do we have? Exactly. Robert just called it out in class here. We have 2 coppers because this guy right here goes to our copper, our Cu right here. These guys are together. So we've got 2 coppers. What about O's? How many oxygens do we have?
1.
1, exactly. And then finally, how many carbons do we have? 1.
1.
1, precisely. So 2, 1, and 1 over on our reactant side. What about if we look over at the product side? How many coppers do we have?
1.
1. The 1 copper right here. How many carbons do we have?
2. No, wait, 1.
There you go, you caught it.
Okay.
Just the 1. Remember, this guy doesn't have any subscripts or anything along with him. So we've just got the 1 carbon. And then finally, how many oxygens do we have on the product side?
2.
2, exactly. This little subscript guy right here is a 2. And he's telling us that in carbon dioxide and CO2, we've got 2 oxygens. So again, not a whole lot of balancing going on. Our carbon looks like he's balanced, 1 and 1 on either side, so that's nice. But our copper and our oxygen are not balanced. We have 2 coppers and 1 And with our oxygens, we have 1 and 2. Neither of those are equal, so we have an unbalanced chemical equation. So in this one, it's kind of tricky to figure out where to start, right? I said last time, start with the smallest one, but these guys are both equally small. So in this case, when there's not really any clear area to start, I like to just work from the first atom written down and kind of work my way down from there. So just because it's the one that we wrote down first, let's try and balance our copper atoms first. So we've got 2 coppers on the reactant side. That subscript we're not allowed to change at all. So is there anything that we could do on the product side to give us 2 coppers?
Add a coefficient or add a coefficient, right? That's what the big ones are called, coefficient.
That's what the big ones are called. So where are we going to put that coefficient?
Before it.
Before the CU. And so what should we change this coefficient into in order for it to be equal?
A 2.
2, precisely. So we already have 2 coppers on the reactant side. So if we make this a 2, then we will have 2 coppers on the product side. So that seems pretty straightforward. Now we have an equal number of 2 and 2, so that's nice. Okay, let's move on to our oxygens. We've got 2 oxygens on the product side. So what can we do over on the reactant side to give us 2 oxygens? Robert says put a 2. Robert, where is that 2 going to go? Well, it's going to go on the reactant side, but is it going to go in this spot or is it going to go in this spot?
Right there.
Here? Remember, we're trying to balance the O. So the beginning? That sounds good to me. So in order to balance this O and give us 2 O's, we could put a 2 right here. So this gives us 2 oxygens on this side. 2 oxygens right there. And so look at that. 2 oxygens on either side. Bingo, bango, bongo. We are all balanced, right?
Yes.
Yes.
Aha. This was a trick. And I have tricked you. So remember, this 2 goes with this oxygen, but it also goes with copper right here. So we do have 2 oxygens, which is good, but we no longer have 2 coppers. How many coppers do we have now instead?
4.
4, precisely. 2 times, remember we multiply when we have the big and little number together. 2 times 2 is 4. So we have now balanced our O's. Yay! But in the process, we made our coppers unbalanced. Ooh. But again, that's okay. This happens all the time when you're trying to figure out chemical equations. So now we have 4 coppers on the reactant side. I don't want to mess with that over here because we've already balanced our O's, and that's a good thing. And so I'm wondering is there anything that we could do on the product side to give us 4 coppers instead of 2 coppers?
Add 2.
So yeah, we need to add 2 coppers. And remember, we can always change the coefficients until we get things balanced. So what coefficient could we change over here on the product side that would give us 4 CUs instead of 2 CUs?
The coefficient, right? The big number before it.
So which coefficient? The one over here?
I want to say yes.
Yeah, because remember, we're trying to change copper, and there's no copper over here. This is a carbon, and this is an oxygen. So we're going to change this guy. And remember, like I said, we can always fiddle with the coefficients until we're satisfied. So just because this is a 2 for now, doesn't mean it has to stay at 2 forever. We could take it out and replace it with something else. And so what would we need to replace it with in order to make it balance the reactant side?
A 4.
A 4. Exactamundo. Now, instead of having 2 coppers on this side, boop, we've changed it. So now we have 4 instead. Just like that. It's that easy. Again, you can always change, you can always erase and add in a different coefficient if that will help you balance the equation.
Okay, I have a question. So
it's balanced. Yeah, go for it.
So the lines before the C, right? That's gonna stay blank, right? Okay, so that was like to throw us off.
Kind of. Well, that's just saying that you could put something here and here if you wanted, but you don't have to. So that's set up on the homework as well. Every molecule, every compound or atom has that blank in front of it, but you might not need to put anything there. You might be able to leave it as a blank and just leave that atom as it started with. Again, we never messed with the carbons at all during this. They started off as balanced and they stayed balanced throughout the whole process. So there's never any reason to mess with the C over here or the CO2 over here. So it's totally fine to leave these spaces blank if you don't have to change the coefficient at all. So let's check and see if we're fully balanced. So we've got, let's see, 2 times 2 gives us 4 CUs on the reactant side. And this 4 right here gives us 4 CUs on the product side. So now that one is balanced. Check, check. We've got 2 O's on the reactant side and 2 O's on the product side. So that is also balanced. Check, check. We've got 1 C on the reactant side and 1 C on the product side. That never changed. So that is also a check. So now we have fully balanced our copper oxide equation. So our final result is 2 Cu2O plus C produces 4 Cu plus CO2. 2 copper oxide plus carbon produces 4 copper plus carbon dioxide. This one needed a little bit more finagling, a little bit more touching up than the other ones. But again, the same process applied. Figure out your starting number of atoms, change a coefficient to try and balance them, see if that has changed any of the other balances, and keep going back and forth, changing the coefficients that make the most sense until you end up with a nice balanced chemical equation here. All right, so that is our process for going through in balancing a chemical equation. Now, the good news that I have for you guys, if you're not still 100% on board with this, is that is okay. Most people don't fully 100% get it the very first day we go through it. And so that is why, A, we did most of the questions on the homework as examples here tonight. And B, I forget if I already mentioned this or not, but the homework is a completion grade. So 3 of those examples that we did are lifted directly from the homework. So let me show you that real quick here. So let me see, go back to actually. Send some stuff around so that we can see it up on the big board here in the classroom as well. There we go. All right. So here is that first example, or the first non-notes example we went over with the calcium and the oxygen. And then we did the one with the nitrogen and hydrogen. And then we did the one with the copper and the carbon that we did just now. So there's one more that we're not going to do here in class that I want you guys to try on your own. The one thing that makes this one a little bit different is that on the product side over here, you have oxygens in 2 different places. So the numbers that you're counting up should include the total number of oxygens. So if you look at the 1 oxygen right here and the 2 oxygens right here, how many total oxygens do we have on the product side of this equation?
Is it 4?
Close, but not quite. This guy is 2, but this guy is 1. So how many total do we have if we put those together?
3.
3, precisely. So on our reactant side, on this side, we're starting off with 3 oxygens. You always have to remember that we take all of one type of atom and add it together. So we have the 1 O right here, 2 O's right here, gives us 3 O's total. So again, do your best to figure that one out. But this is a completion grade, which means that as long as you try and put down an answer on all of these equations, even if it is not the correct answer, you'll still get full credit on the assignment when you turn it in. So I think this is a 5-point assignment. As long as you turn it in and you've tried to answer all the questions, even if you have some wrong answers on there, you'll still get 5 points for the assignment. Again, normally we would spend like a couple full class days going through this, doing lots of examples, making sure everybody is okay with it. But unfortunately, since we only meet 2 days a week, we only have 1 day to work on this together before we have to move on to the next stuff next week.